California is shaking all the time. Tiny earthquakes happen there constantly. Most people never feel them. Little bursts of movement deep underground. A reminder that the earth beneath the state is never truly still. And honestly, that constant activity usually makes scientists feel better. Because active faults release pressure. Small earthquakes are normal, expected, healthy in a weird geological sort of way. But recently, seismologists started noticing something strange along part of the San Andreas Fault. A section of the fault had gone unusually quiet. At first, it didn't seem like a huge deal. Earthquake patterns fluctuate naturally all the time. Fault systems are messy, irregular. But the silence kept going, and some researchers started asking an uncomfortable question. What if the fault isn't relaxing anymore? What if it's locking? Because deep underground, silence can be dangerous. The San Andreas Fault stretches roughly 800 miles across California. It cuts through mountains, deserts, forests, farmland, and major cities. It's one of the most famous fault systems on Earth, and one day it will rupture again. That part isn't speculation, it's certainty. The only question is when. Scientists sometimes describe earthquakes in unsettlingly simple terms. A fault accumulates stress slowly over time, until the rock can't hold it anymore. Then suddenly, it breaks. Years of pressure release in seconds. That's an earthquake. And the worrying thing about locked fault sections is that they may continue storing stress quietly for decades. Just pressure building underground while life above continues normally. Cars moving through Los Angeles traffic. People surfing along the California coast. Office towers glowing at night. Millions of people living directly above one of the most dangerous fault systems in North America, completely unaware that scientists are paying attention to what isn't happening beneath them. Because sometimes, the absence of earthquakes means a fault is sliding harmlessly. But sometimes, it means the fault has stopped moving altogether. And if stress keeps building inside locked rock, eventually the Earth reaches a point where it can't absorb any more pressure. That's when faults break violently. The scary part is that California has seen this before. Back in 1906, the San Andreas Fault unleashed one of the most devastating earthquakes in American history. The rupture tore across hundreds of miles of California in less than a minute. The ground moved so violently that fences bent sideways, roads split apart, entire sections of San Francisco collapsed and burned. And scientists today believe parts of the fault may once again be entering conditions capable of producing another major rupture. Modern instruments now monitor California with unbelievable precision. GPS networks measure tiny ground movements across the state. Seismic sensors detect vibrations smaller than human perception, and the data tells a strange story. Some sections of the San Andreas are still creeping gradually, releasing pressure little by little. Others appear increasingly locked, like giant pieces of the earth getting stuck against each other underground. That's what keeps seismologists awake at night. Not the earthquakes they can see, the stress they can't. Because somewhere beneath California right now, the Pacific Plate is still pushing northward. The North American Plate is still resisting. The fault is still under pressure, and in at least one unusually quiet section of the San Andreas system. The silence may not actually mean stability at all. Most people think of the San Andreas Fault as a crack in the ground, like a giant fracture slicing through California. But that's not really what it is. The San Andreas is actually a boundary between two enormous pieces of Earth's crust, two tectonic plates. And those plates are constantly trying to move past each other. On the other sits the North American Plate, and they absolutely do not move smoothly. That's the problem. The Pacific Plate is slowly grinding northwest relative to the rest of North America, at roughly 2 inches per year. That doesn't sound like much. Honestly, it sounds harmless. But geology works differently from human intuition, because the plates don't glide past each other cleanly. The rock along the fault gets stuck due to friction. Stress starts building underground as the plates continue trying to move anyway. Imagine dragging two gigantic, rough concrete slabs against each other. At first, nothing happens. Pressure builds. The slabs lock together. Then suddenly, they jerk violently. That violent release is an earthquake. And California sits directly on top of that system. The really strange part is that the San Andreas Fault is actually shaping California itself. Los Angeles, for example, is technically moving northward over geological time because it sits on the Pacific Plate. Very slowly, over millions of years, Parts of Southern California are literally sliding toward San Francisco. It sounds ridiculous, but it's true. California exists because these tectonic forces have been grinding against each other for tens of millions of years. Even the landscape itself has been sculpted by fault movement. And the fault is not one single clean line either. That's another common misconception. The San Andreas system is messy, complicated. It branches into smaller faults, interconnected fractures, creeping zones, locked zones, deep stress fields. Some parts move gradually all the time. Others remain frozen for decades or centuries before rupturing violently. The Earth down there is constantly adjusting. That's why earthquakes are so difficult to predict. Fault systems don't behave like machines. They behave more like stressed living systems. Sometimes pressure releases in small, harmless quakes. Sometimes faults creep slowly without major shaking. And sometimes, stress accumulates silently for years before everything breaks at once. Scientists have spent decades trying to understand which sections of the San Andreas are most dangerous. One area researchers focus on heavily is the southern segment of the fault. Because unlike some northern sections that release energy more frequently, parts of Southern California's San Andreas appear heavily locked, meaning the plates aren't sliding past each other efficiently anymore. They're resisting, holding tension underground. And tension is basically stored energy. The longer stress builds, the larger the potential release can become. That's why seismologists sometimes compare faults to stretched rubber bands. The more force applied over time, the more violent the snap may eventually be. And according to geological evidence, some sections of the San Andreas may already be storing enormous amounts of stress. Researchers study this using all kinds of tools: seismic sensors, satellite measurements, GPS deformation maps, even trenches dug across ancient fault ruptures to study prehistoric earthquakes buried underground. And one thing becomes very clear when scientists examine the San Andreas over long timescales. California's modern cities just happen to exist during one of the quieter periods. That's an uncomfortable idea for a lot of people, because modern California feels permanent, stable, massive highways, skyscrapers, suburbs stretching for miles, millions of people building lives on top of a fault system that has repeatedly produced catastrophic earthquakes throughout history. The earth beneath them doesn't care about any of that. The plates keep moving anyway, day after day, year after year. Even during complete silence underground, the motion never truly stops. That's what makes the recent quiet sections along the fault so unsettling to scientists, because silence does not necessarily mean inactivity. Sometimes it means pressure is transferring deeper into the system. Locked rock may continue deforming invisibly underground while the surface above remains calm. And the San Andreas has a long memory. Some sections rupture every 100 years or so. Others wait much longer. But eventually, stress reaches a point where the fault can no longer hold itself together. Then the landscape changes violently in seconds. Roads twist, power grids fail, ground shifts sideways. Entire cities suddenly realize the earth beneath them was never stable to begin with. That's the strange psychological reality of California. People live normal lives on top of one of the most studied fault systems on Earth. And despite all the satellites, sensors, and seismic models, scientists still cannot say exactly when the next major rupture will happen. They only know the pressure underground is still building, quietly, relentlessly, every single day. Usually, California sounds alive underground. Not literally, of course, but to seismologists staring at monitoring screens all day, the Earth is constantly talking. Tiny tremors, microquakes, low-level seismic chatter, the planet releasing pressure in little bursts over time. That background activity matters more than most people realize, because faults that move regularly tend to relieve at least some stress gradually. Not enough to stop large earthquakes completely, but enough to keep the system from locking too tightly. That's why scientists became uncomfortable when parts of the San Andreas started going unusually quiet, especially along certain locked segments in Southern California. The issue wasn't one missing earthquake, it was the pattern, or rather, the lack of one. Some researchers noticed stretches where seismic activity appeared lower than expected, compared to historical behavior in surrounding regions. Tiny earthquakes that normally occur as stress adjusts underground seem strangely absent. Most people hear that and think, great. Seismologists hear that and sometimes think, that's weird. Because faults are supposed to move, even a little, especially active faults like the San Andreas. When movement slows too much, scientists start asking whether stress is becoming trapped instead of released. That's where the phrase seismic gap comes in. A seismic gap is basically a section of fault that has remained unusually quiet compared to neighboring regions or historical patterns. Sometimes those gaps are harmless. Sometimes stress is releasing through slow creep underground without noticeable earthquakes. But sometimes the fault may be locked. And locked faults are dangerous because the plates continue trying to move anyway. Imagine bending a thick branch slowly. At first, it flexes. Tiny cracks form inside the wood. Pressure spreads unevenly, but from the outside, nothing dramatic happens. Then, eventually, the branch snaps all at once. That's essentially what seismologists fear with heavily locked fault zones. The Earth looks calm at the surface, while underground stress keeps accumulating year after year. Researchers studying the San Andreas use GPS systems capable of measuring ground movement with astonishing precision. Some instruments can detect shifts smaller than a fingernail across huge sections of California, and the measurements reveal something unsettling. In certain regions, the crust on opposite sides of the fault continues deforming. The plates are still pushing, still straining against each other, but the fault itself isn't releasing that energy efficiently, meaning stress may be building deeper underground, quietly. That's the part most people misunderstand about earthquakes. The real danger often develops long before the shaking starts. The earthquake itself is just the release. The actual process begins decades earlier, while stress accumulates invisibly inside locked rock. And Southern California may contain some of the most stressed sections of the entire San Andreas system. One particularly concerning stretch lies near the southern end of the fault, not far from the Salton Sea. Geological studies suggest this section hasn't experienced a major rupture since sometime around the late 1600s or early 1700s. That's a very long time for an active plate boundary, especially one moving several centimeters per year. Over centuries, that missing movement adds up. The plates keep trying to slide, the fault keeps resisting, the stress keeps growing. Scientists sometimes call this a slip deficit. Basically, the Earth owes movement that hasn't happened yet, and eventually, physics tends to collect the debt. That doesn't mean a catastrophic earthquake is guaranteed tomorrow, or next year, or even this century. Fault systems are complicated. Some locked zones may partially release stress through smaller, hidden deformation processes scientists still don't fully understand. But uncertainty itself creates tension, because researchers know enough to recognize warning signs, while also knowing they cannot predict exactly how the fault will behave. That's what makes the silence psychologically disturbing. Humans usually fear obvious danger, but the San Andreas threat is almost invisible. Millions of Californians wake up every morning above a fault system that may be storing enormous amounts of underground energy without producing much obvious activity at all. Life continues normally. Coffee shops open. Traffic floods the freeways. Office buildings sway gently in ocean winds. Meanwhile, beneath all of it, two tectonic plates continue grinding silently against each other, still stuck, still building pressure. And the longer some sections remain quiet, the more uncomfortable certain scientists become. Because deep underground, silence does not always mean peace. Sometimes it means the fault is holding its breath. The uncomfortable thing about earthquake science is that researchers often recognize danger long before they can do anything useful about it. That's basically the situation with the San Andreas Fault. Scientists can see stress building. They can measure deformation. They can map locked sections underground. But they still can't tell people exactly when a major rupture will happen. And honestly, that uncertainty drives everybody crazy, especially in California, because California is one of the most heavily monitored geological regions on Earth. Thousands of seismic sensors are spread across the state. GPS stations continuously track ground movement. Satellites measure crust deformation from orbit. Scientists have more data on the San Andreas than almost any fault system in human history. And the data keeps pointing toward the same uncomfortable reality. Large sections of the fault are still under enormous stress. Researchers sometimes describe California as being slowly squeezed and twisted by tectonic forces every single day. The motion is tiny from a human perspective, a few centimeters per year, barely noticeable. But over decades, centuries, That movement accumulates into huge amounts of stored energy underground. And some sections of the San Andreas appear to be absorbing that energy without releasing much of it through smaller earthquakes. That's where things start getting concerning. One major clue comes from GPS deformation maps. Scientists can literally watch parts of California moving in different directions over time. The Pacific plate keeps trying to slide northwest. The North American plate resists. Meanwhile, the crust between them bends and deforms under pressure. It's almost like watching the Earth slowly winding itself tighter. Researchers studying fault behavior compare this process to stretching elastic material. At first, the system absorbs stress gradually, but eventually, the material reaches a breaking point. Rock behaves similarly underground. It flexes slightly under pressure. Microscopic fractures spread. Stress redistributes through fault networks. Then at some point, the rock fails catastrophically. That's an earthquake rupture. And the terrifying part is how fast the transition happens. A fault may remain locked for centuries, then release massive energy in under 2 minutes. That's what happened in 1906. That's what scientists know will eventually happen again, somewhere along the San Andreas system. The real argument is about timing and magnitude. Some researchers worry the southern section of the fault may now be capable of producing an especially large rupture because of how long stress has accumulated there. And unlike Northern California, Southern California contains enormous urban density directly near the fault system. Los Angeles, San Bernardino, Riverside, millions upon millions of people, critical infrastructure everywhere, highways, aqueducts, electrical transmission lines, internet infrastructure, fuel pipelines, rail systems, modern civilization layered directly across an active tectonic boundary. That's why certain scientists have started using unusually blunt language in interviews over the past decade. Not panic, not sensationalism, but realism. You'll hear phrases like, "It's not a matter of if, but when." Because from a geological perspective, the next major San Andreas earthquake is inevitable. The fault is still active. The plates are still moving. The stress is still accumulating. And the silence in some locked areas may mean the system is storing even more energy underground. One thing researchers particularly watch is fault creep behavior. Some parts of the San Andreas creep continuously, sliding little by little without major earthquakes. That's generally safer because movement gets released gradually. But other sections remain stubbornly locked. Those locked zones behave differently. Instead of releasing stress continuously, they hold on to it, sometimes for generations. Scientists also study prehistoric earthquakes by digging trenches across old fault ruptures. Inside the soil, they can identify layers displaced by ancient earthquakes hundreds or even thousands of years ago. It's strange work, almost like forensic geology. And those buried records show a disturbing pattern. The San Andreas has produced massive ruptures repeatedly throughout history, long before modern California existed, long before skyscrapers, long before freeways and power grids. The fault does not care about civilization. It follows physics, and physics suggests stress eventually releases, sometimes violently. That's why the recent seismic quietness feels so eerie to many researchers, because faults don't necessarily become safer when they stop producing small earthquakes. Sometimes the opposite is true. Sometimes silence means friction is increasing. Sometimes silence means the plates are locking harder against each other underground. And when enough stress builds inside locked rock, the eventual rupture can become catastrophic. Still, scientists are careful not to overstate what they know. Earthquake prediction remains one of the hardest problems in science. No sensor can tell researchers the fault will break next Thursday. The Earth simply doesn't behave that neatly. There are too many variables, too many interacting fault systems, too many unknowns deep underground. But uncertainty itself creates tension. Because modern California now exists in a strange psychological state. Everybody knows the big one will happen someday. Nobody knows when. And beneath the cities, highways, beaches, and suburbs, the San Andreas Fault continues moving silently through the dark, still locked in places, still building stress, still waiting. At 5:12 in the morning, on April 18, 1906, most of San Francisco was still asleep. Then the ground started moving, hard. Not a gentle tremor, not the kind of shaking Californians joke about today. This was violent. Buildings lurched sideways almost instantly. Brick walls exploded into the streets. Chimneys collapsed through rooftops. People were thrown from their beds before they even understood what was happening. And beneath the chaos, the San Andreas Fault was ripping across California. For nearly 300 miles, the earth itself ruptured open. Fence lines suddenly shifted sideways by more than 20 feet in some areas. Roads twisted apart. Railroad tracks bent like wire. The rupture moved so fast underground that the landscape physically changed in under a minute. Imagine standing outside and realizing the ground beneath your feet is literally sliding sideways. That's what happened. And honestly, the earthquake itself was only the beginning. Back then, San Francisco was packed with wooden buildings, gas lines, and primitive infrastructure. Once the shaking damaged the city's water system, fires started spreading almost immediately, and nobody could stop them. For 3 days, huge sections of San Francisco burned. Entire neighborhoods vanished into smoke and ash. Some people escaped the collapsing buildings, only to find the city itself catching fire around them. Eyewitness accounts from 1906 still feel disturbing to read today because of how surreal everything became so quickly. People described streets rolling like ocean waves, church bells ringing on their own, the sound of collapsing masonry echoing across the city in darkness and smoke. One survivor later said it felt like the earth had turned liquid, and in some places, it basically had. The shaking caused soil liquefaction in parts of the Bay Area, where water-saturated ground temporarily lost strength and behaved almost like mud. Buildings tilted, roads cracked open. Modern scientists still study 1906 constantly because it revealed something terrifying about the San Andreas Fault. The system was capable of producing enormous rupture lengths. That matters. Because earthquake magnitude isn't just about how hard the ground shakes. It's also about how much of the fault breaks at once. And in 1906, the rupture spread across a massive section of California. The earthquake released decades, maybe centuries, of accumulated tectonic stress in seconds. Researchers today estimate the quake reached roughly magnitude 7.8, possibly higher. At the time, scientific instruments were primitive compared to modern standards, so exact numbers remain debated. But one thing is absolutely clear. California was completely unprepared. And honestly, in some ways, it still is. Modern California has stricter building codes now. Seismic engineering improved dramatically after major earthquakes throughout the 20th century. But modern civilization is also vastly more interconnected. That creates new vulnerabilities. In 1906, there were no massive electrical grids spanning the state. No internet infrastructure, no millions of cars dependent on elevated freeways, no giant logistics systems moving food, fuel, and water across California every day. Today, a major rupture would hit a society far more technologically advanced and far more dependent on fragile infrastructure. That's why scientists studying the San Andreas often revisit 1906 psychologically, not just geologically, because the earthquake permanently changed how Californians viewed the ground beneath them. Before 1906, many people barely understood faults at all. Afterward, the illusion of stability disappeared. The earth beneath California was not solid. One of the strangest things about the 1906 rupture is that it temporarily reduced earthquake stress along parts of the northern San Andreas afterward. Some sections entered quieter periods for decades, but stress transfer in fault systems is complicated. Releasing pressure in one area can increase pressure somewhere else. That's another reason scientists monitor Southern California so carefully now. Because parts of the southern San Andreas did not rupture during 1906, meaning some stress may have continued accumulating there across generations. Researchers analyzing geological trench data discovered evidence that certain southern fault segments may have gone unusually long without major rupture. Again, that word shows up: quiet. And in earthquake science, quiet can become deeply unsettling. The longer locked faults remain stuck, the more elastic strain may accumulate underground. Eventually, the rock reaches a limit. Then the fault breaks. That's the cycle California lives with. Then the cycle begins again. Most people don't think about it during normal life. And honestly, how could they? California feels alive. Millions of ordinary moments happening every day. People walking beaches in Santa Monica. Traffic crawling through Los Angeles at sunset. Kids going to school beside palm trees. Office towers glowing across San Francisco Bay. Meanwhile, beneath all of it, The San Andreas Fault remains exactly where it has always been,